So welcome. So this is linear momentum and collisions, and we touched on this last time. We recognize that if we want something to be consistent from the beginning of a collision to the end of a collision, we've got to look around for it. And what we came up with was momentum, this mass times velocity. In colloquial terms, we'll talk about having the momentum, which means that a game is going your way or whatever. But what we specifically mean is that momentum is mass times velocity. Velocity is a vector, mass is a scalar, multiply a scalar by a vector and you get a vector. So momentum's a vector. And then we linked it to good old Newton, and we realized that Newton spoke in terms of momentum. He didn't talk in terms of accelerations. And then we actually got to the stage where we started touching upon impulse and momentum. So let's just look at that briefly. So P equals mv, P's a vector, V's a vector. And then we said with good old Newton, Newton said the sum of the forces is not equal to ma, is equal to dp by dt. Change in momentum with time. And then we talked about impulse, and we said, well, if I have an acceleration that is applied for a longer time, I get more change in my velocity because the acceleration acts for longer. So time does matter, or duration we tend to call it, does matter. And so we'll develop this term called impulse. And impulse is defined as the force times the duration. If a variable force over time, then I've got to do a sum of all the little bits of forces multiplied by the little bits of time. And so I have an integral. So impulse equals the integral of f dt, a bit like work equals the integral of f dx. It's the same kind of idea. And what we have is that we shove it in and we say, oh, well, look, impulse equals my change in momentum. So we had, and this is where I think people have to be a little bit careful, because what I've noticed in the past is people tend to get a little bit confused, that force is equal to dp by dt, but impulse equals change in momentum. And they're similar enough that people sometimes get them confused. Okay. So watch out for that. This is called the impulse momentum theorem, and basically it's another tool in our toolbox. Did we do these last time? I can't remember. A particle is acted on by a force of 12 newtons that acts in a negative direction. Force acts for 5 seconds. What's the impulse? I'll do them anyway. So we have this particle, force of 12 newtons that acts in a negative direction. I do my forces in line with the object. I do my velocities and my accelerations above or below. That's my shorthand. And my time, put my time in a clock, so in a little round clock. 5 seconds, and then what's the impulse? And impulse, 3 lines means defined as. Impulse is defined as the integral of f dt, which in simple terms for a constant force is equal to f times t. So impulse is equal to minus 12. It is a vector, so the direction matters. Minus 12 times 5, which equals minus 60. And, well, what are the units going to be? Well, force is measured in newtons, and t is measured in seconds. So we have newton seconds. And, okay, it's a vector, so I can do 3-dimensional stuff, so I can do ijk stuff. And I say, here's my particle. Is acted on by a force, and the force is F is equal to, it's a vector force, so F is equal to 3I plus 2J plus 4K. That's going to be in newtons. And this is acted on for 4 seconds, so my little clock says 4 seconds. And what is the impulse of this? And I say, well, my impulse is defined as the integral of f dt, which equals my force multiplied by my, I really should put down delta t actually, because it's a time interval, isn't it? So it's better to put down delta t than just t. T implies a time on a clock. Delta t implies the change of time on a clock. And we let it go for 4 seconds, not at 4 seconds, but for 4 seconds. And so it should be a delta t. But this is, so impulse is equal to, my force of course is equal to 3I plus 2J plus 4K. And my time is 4 seconds. So my impulse is equal to, this is my vector impulse, is going to equal, it's going to be 12I plus 8J plus 16K. And we still need units, so the units are Newton seconds. So there we have it. Don't forget, you need units even if it's an IJK vector. You can't just ignore units. People tend to either always put units down, or they tend to just blowing units away. Occasionally people are stressed. I can tell if they're stressed, if they find a problem hard, especially towards the end of a test, because they'll occasionally miss units. But by and large, most people never miss a unit, or they miss pretty well all of them. And that's the habit I've got to break you of if you're like that. Got to break you of the habit of just forgetting units. A stationary particle is acted on by a force of 7 newtons. It acts in a negative direction. Negative what direction? Okay, so we have, stationary particle. It acts in a negative direction, so that's minus 7 newtons. The force acts for 3 seconds, so my time is, my delta t is 3 seconds. What is the particle, what is the particle's momentum after this action? So I want to know my P. What did we say? P is equal to, I is equal to dP. So I is equal to P final minus P initial. I is equal to MV final minus MV initial. I'm actually trying to find P final, so I can leave that as a P final, but I might need the MV for the first bit, or maybe not. And of course I is also equal to the integral of f dt. So I is equal to, in a straight line when there's a constant, everything is force times my delta time. So my force times my delta time equals mv final minus mv initial. And let's see what I know. I know that's minus 7, and I know that's 3 on that side. And then on this side, mv final, well actually I want p final, so let's just put down as p final minus mv initial. Well, I'm not told what the initial momentum is, and I'm not told what the mass is, but I am told that the particle is stationary to begin with. And so because I'm told it's stationary to begin with, I know my initial velocity is 0. So whatever the mass is, if I multiply it by 0, it becomes 0. So that information is kind of hidden away there. So P final is equal to minus 21. And what the unit's going to be for momentum? Well, they're going to be mass times velocity. So kilogram meters per second. So minus 21, not 21, but minus 21 kilogram meters per second. So I just took the mass, the momentum, impulse momentum theorem, and I applied it. And yeah, it's a little bit wrinkly, you know. I needed to know that momentum was mass times velocity to get the significance of that stationary particle. But I wasn't asked for the velocity final. I was asked for the momentum final. So there was no need for me to give you the mass. You know, what you do is, let's say you didn't spot that that was 0, or you didn't know what to do, even if you spotted it was 0. You kept saying, "What's the mass?" Then what you can do is, my advice is, if I'm not giving you something you think I should be giving you, and all else fails, you've left it until the end of the test and you still can't figure it out, bung in a number, bung in 1, bung in 5, just stick a number in there and try and work the problem and see what you come out with. Sometimes it happens more and more we get to the stage where you don't actually need something because it cancels. Mass often cancels. And so later on, I can do problems where I don't need to give you the mass. In fact, I need to give you very little information. We'll see some of those later. And people will go, but I don't have the mass. How can I find the kinetic energy when I don't have the mass? And I'll go, just do your best. And the reason is because that mass is going to cancel on the other side of the equation. So you don't need the mass. The mass is irrelevant in it. But, you know, and this is what's going on here. This is the tradition inside the program, not just my program, but, you know, the community of trying to get people to write in sentences. Yeah, I know that impulse equals force times my time interval. So I could have done that calculation over there and not linked it to the change in momentum. You know, momentum's over here, so-and-so's over there. At some point I'm going to try and get them together, but I'm thinking in phrases. I'm thinking in just partial sentences and not putting them together. Not thinking in terms of a sentence is an equation. It's a beginning, a middle, and an end. It's got an equal sign in it. So if you're not writing down stuff with equal signs in it, then be wary because you're not thinking about the principal equation that guides things. You're thinking about little amounts of stuff, and then you're going to try and link them in your brain somehow. And that's when you get caught out because you can't find your kinetic energy because you don't have the mass, and you can't find something else because you don't have the mass, and then you don't put them together. You don't realize the mass just cancels out. So watch out for that. Okay, let's go three-dimensional. This is a derivation. The important thing is that the momentum finally equals the momentum collision. Let's talk about a collision. If I'm in a collision, then there's a couple of things to realize. First of all, I push on you as hard as you push on me. Big car and a little car and a big truck, doesn't matter. Love bug and your vehicle push on each other just as hard. There's a different outcome because the masses are so different, but the forces are an action-reaction pair, equal and opposites. So the force of one is equal to the force on the other. And so I can turn around and say, and the duration, I touch you for as long as you touch me. I can't touch you for a little bit and you touch me for longer. It's like wherever we're touching, we're touching. So what that means is, consider a two-particle system. The force of 1 on 2 is equal to the force of 2 on 1. And if we remember, the force of 1 on 2 is dp2 by dt. I'm just saying force equals change in momentum. And force equals change in momentum. And I know that these guys are equal and opposite. So I can say they're equal and opposite. If I sum them, there's no overall change. You know, plus 6 added to minus 6 is 0. So if I sum them, they're 0. So express it in dp by dt. So dp by dt for the first plus dp by dt for the second is d by dt of the first plus the second, and that must sum to 0. So great, because I know these, that is that, and that is that, and the answer is 0, and the answer is 0. So what that says is that change in momentum equals 0. So this means that the total momentum of a system is constant. P initial equals P final. That's the take home. You can always rely on your mom to be the same. Okay? She doesn't change. Neither does momentum. Okay? So momentum is constant. Now, not for a given particle. If I'm in a collision, my momentum is going to change a lot. But for the system, for the two particles, the overall momentum, the sum of the momentums doesn't change. Okay? That's always true. Not all collisions. That's always true for every collision. We're going to talk in a bit, like in a second, about kinetic energy. How many people have been in a kind of like car crash? How many people have been in a car crash? Physically speaking, what's your physicality? What's your recollection of the instant of the collision? What do you, when you think about it, what do you remember?
Going forward.
Pardon?
Going forward.
Well, you must have stopped doing that. Oh, you got jerked forward. You got hit from behind. Okay. Anything else?
Why do you go forward?
Yeah, but I'm thinking about senses. What are your senses? What do you feel in your senses? Pardon?
Pressure.
Pressure, force over an area. Anything else? How do you know that an accident's taken place if you're not in it?
Initial force.
If you're not in it?
The sound. Oh, the sound.
The sound. That's energy leaving those two cars. My recollection is the sound and the heat. I felt this like wave of heat. It was like I was in the back seat, and I was on the side where we got T-boned basically, and it was a cab. I saw it coming. It's like I said, because this big yellow cab is coming over, it's going to hit us. And I said to the guy who was driving, I say, be careful. So polite when I think about it. I say, be careful. Yeah. And I remember the heat and I remember the sound. And for a long time afterwards, if I was getting a shower, I'd kind of like flinch because it was like the sound was there. There's so much energy been leaving the system. That's what you want. That saves lives. More energy. I wish collisions were like 10 times louder because, man, you dissipate more energy. Most of the energy goes into the crinkle zone. One of my biology teachers bragging about the fact that he's in a collision with a Honda, and there's hardly a scratch on my pickup truck, but the Honda's written off. And I'm going, yeah. And the driver in the Honda had all that energy absorbed, and you're like an egg in a box, you know? I mean, yeah, your truck was hardly scratched. You had no crumple zones. You got an old truck. It's got not as safe as anything. Chances are you're going to get hurt if you're not careful. If he hits something that's similar size, he's done for. So yeah, you want crumple zones. So we have this weird situation where kinetic energy is not conserved. I mean, you know that because in the end, well, let's not be careful about that. No, you don't know that because everything stops. But kinetic energy is not conserved, and you know that because of the sound and the heat and all that kind of stuff, yeah? So, all right. So we can't rely upon kinetic energy. Well, most of the time we can't rely upon kinetic energy. It turns out that gas molecules, kinetic energy is conserved. If I have electrostatic particles, kinetic energy is conserved. All that kind of stuff. So I have two basic classes of collisions. I have collisions where kinetic energy is not conserved, and these are called inelastic. Inelastic and inelastic. And then I have collisions where kinetic energy is conserved, and these are called elastic. And it's a good idea to have some visualizations to this. So billiards or pool, whatever you want to call it, that's pretty good approximation. All you hear is, you know, the balls don't get any hotter, they don't crumple. You know, that's all the energy is given off. So that's pretty good combination. And then we have, that's for the elastic. And then for the inelastic, there's two examples that I think of. Fender bender, where the car's mangled a bit, but the two cars don't stick together. You know, I hit you, you hit me, we bounce apart, you know, whatever. Or a rugby tackle, where the two objects combine. That would be. And the difference between those two is that in the perfectly inelastic, in the rugby tackle, you know the two masses have the same velocity at the end. Whereas up here, you don't know the two masses have the same velocity because they don't. Maybe coincidentally they do, but they typically don't. So in principle, momentum is conserved and kinetic energy is conserved. In principle, only momentum is conserved. And then there's this little wrinkle that if it's a perfectly inelastic collision, the two objects stick together, and so you know they both have the same final velocity. By the way, an explosion is the opposite of this, if you think about it. Take one object made of two bits, you end up with an explosion. There's other ways you can dress it up. I'm stuck in space. My spaceship is over there. I'm on a spacewalk. I've run out of gas for my little gas-propelled jetpack. How do I get back to... I'm 20 feet away, but, you know, swimming's not going to do any good because there's no friction in space. So I'm going to float next to my little space capsule for the rest of eternity, 20 feet away. You know, I'm going to grow old. Well, I'm going to starve first, aren't I? But it's going to be so close and yet so far. And what would you do? And one of the things you can do. Anybody know what would you do? You're out. You got your wrenches and all that. You are fixing something, and you know. Let's say you're fixing a satellite, and the satellite is there, but your spaceship is there, and you go to fly back, and it doesn't happen. So what would you do? Yeah, you take your backpack, or you take your tools, or the satellite, whatever. And if I throw it in that direction, because of conservation of momentum, there's zero momentum along this line to begin with. If I give that a positive momentum, I got to have a negative momentum, which means I have a negative velocity going towards this guy. So it's a little, and that's what explosions do. When I was a student, you can tell how naive I was as a student. I remember telling my buddy that I hoped on, you know, some lab test we were having that we got the question about elastic collisions, and my buddy said, "Why?" And I said, "Well, there's two equations to pick from." And he kind of just smiled at me and said, "Oh, yeah, that's true, yeah, like that." Naive. Why was I so naive? Because teachers will always give you, when you get two equations, simultaneous equations, I'll give you two unknowns in that one. So you don't have two equations to pick from. It's two equations that you need. So let's look at that. Two equations. This is definitely a momentum equation. That's a momentum equation. This is a momentum equation. This is not kinetic energy. This is about velocities. So what's going on? It turns out, and you might want to try this. I mean, I would just try it one time. Try and solve a elastic collision problem using conservation of kinetic energy with a half mv squared. So it wouldn't be this, it would be a half m1 v1 initial squared plus a half m2 v2 initial squared equals a half m1 v1 final squared plus a half m2 v2 final squared. Yeah. So it'd be like complicated. And then try and combine that equation with this equation, the momentum equation, and solve it. It's a pain. And then someone came along and said, yeah, no, we can solve this a bit easier by saying the difference in the velocities before the collision is the negative of the difference in the velocities after the collision. So the order matters. So V1 initial minus V2 initial is the negative of V1 final minus V2 final. You combine those two together, much more manageable, and you can solve the problem. So watch out for that. Particle, 7 kilogram particle with a velocity of 4 meters per second collides inelastically with a 2 kilogram particle with a velocity of minus 3 meters per second after collision. The 7 kilogram particle has a velocity of that. Remember, I'm tied by math. I can't magic things up. So if there's only one equation, you can only have one unknown. It's simple as that. So I draw my picture before. So my principle is P initial equals P final. So I say M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Let's draw a picture of it. So this is my 7 kilogram mass, and it's going at 4 meters per second, so that's going to be a plus 4 meters per second. And it's going to combine with a 2 kilogram mass, which is going in the opposite direction, going at minus 3 meters per second. And that's going to equal my 7 kilogram mass. And it says, what is the velocity of the 2 kilogram mass after collision? After the collision, the 7 kilogram particle has a velocity of plus 2. So this has been reduced in speed to plus 2 meters per second. And so here I have my 2 kilogram mass, and I don't know what that is. I could call it V2 final, but it's only letter left, so let's just call it V. So I say, well, okay, 7 times plus 4 added to 2 times minus 3. And now I'm looking at my diagram. I'm not looking up at the words. I'm looking at my diagram. Is equal to 7 times plus 2 added to 2 times V. So I go 7 4s are 28 added to minus 6 is equal to 14 added to 2V. So I get 2V is equal to 28 minus 6, that goes to the other side, minus 14, which equals 28 minus 20, I think, if I did that right. So 2V is equal to 8. So V is going to equal 8 over 2, which equals 4 meters per second. And I got to be plus 4 meters per second. It's a velocity, so plus 4 meters per second. And shame on me, man, unless I'm really messed up on that, didn't I? That's in that direction, and that's going to be plus 4 meters per second. Did I do that right? 28 minus 6 is 22. Minus 14 leaves me with 8. And that, yeah, I did that right. It's right sign. So what happened is we had this one going to the right, and we had the 2 kilogram going to the left, and they ended up both going to the right. And that, you know, the little car usually gets kicked around by the big car. So straightforward principle, you know, keeping track of things, I suppose, is the issue. But I'm tied by the math. I can't give you 2 unknowns without 2 equations. So one way or another, I'm giving you some. I might say, yeah, M2 was stationary, I suppose. I could say that, in which case there's not a number down, but I've got to tell you one way or the other. 3 kilogram particle has a velocity of plus 3 meters per second. Bad teaching there, because it's not good when you're trying to explain things to have the same number, but, you know, forgive me that. Is inelastically, it's perfectly inelastically with a 2 kilogram particle that has a velocity of minus 4, so that's minus 4 meters per second. And what is the velocity of the combination? I can be really tricky here. I can turn around and say, what's the velocity of the combination after the collision? That kind of gives it away. Apart from saying it's perfectly inelastic, that kind of gives it away. You know, it underlines it. It's perfectly inelastic, buddy. That means that the 2 masses stick together, because I said the combination. But I could ask you the same question and say, well, what's the velocity of the 3 kilogram block? And not tell you they stick together. I mean, I told you when I said perfectly inelastic, but I'm not going to emphasize it. So I could say, oh, what's the 3 kilogram velocity? Or what's the 2 kilogram velocity? Could do something like that. So it's not going to always have the same words, and I'm not going to make it sort of as crystal. So that goes to that. So P initial equals P final. M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 V final. People say, why do you write that down every time? Because I want to remember it when I do a test. If I don't practice writing it down, I'm not going to write it down in a test. And I'll tell you, there's nothing more kind of like dispiriting than seeing a section that's filled with numbers, not an equation in sight, and the answer's wrong. It's like, now I've got to go through this, I've got to unravel what somebody did. And or sometimes I can't figure out what they did. It's just, I have no idea what they did. It doesn't really follow what they did. And other times it does, but they made a mistake. And to give them credit, I want to find out what mistake they made. That takes me an age to do that. So after a while you start saying, no equations, I'm going to look at it, and if I can't see what you did, I'm out of here, because I got 30 other people that need grading. So the more you write down when you have open-ended questions, the more you help the examiner grade you, the more times when the shades are grey, the person will spend more time with your paper. And they're not going to spend more time to take points away, they're going to spend more time to add points. So I doubt you're going to have multiple choice tests like in the future. I hope you don't. I hope you don't go to junior and senior class and have multiple choice. I mean, it's like, so I think those days are over. So develop the technique of maximizing your capability in an open-ended question, and a lot of that is communication. So write down this stuff, put this stuff down, practice it, and it'll just become second nature. So I say, okay, that's going to be 3 times plus 3 added to 2 times minus 4 is equal to, and I put down 3 plus 2 because I want to be able to double check and say, oh yeah, I did add them together. I didn't multiply them, which people sometimes do. I did add them together, and it's times V final. So that's going to be 9 added to minus 8 is equal to 5V final. So V final, 5V final is equal to 9 plus minus 8 is plus 1. So VF is equal to plus 1 over 5, which equals plus 0.2 meters per second. So it goes really slowly after the collision. They're almost balanced. 3 3s are 9 in a positive direction, 2 4s are 8 in a negative direction. The momenta before are almost balanced. If they were perfectly balanced, it would just be stationary at the end. A little object can stop a big object if the little object's going really fast and the big object is going really slow. So the trick for that is to pick up on perfectly inelastically. There is no perfectly elastic. There is elastic, there is inelastic, and then perfectly inelastic. But there's no perfectly elastic. 2 kilogram particle with a velocity of plus 5 meters per second. 2 kilogram plus 5. Collides elastically with a 4 kilogram particle. 4 kilogram particle with a velocity of minus 3 meters per second. That gives the 2 and the 4. Let's call this V1 final, and let's call this one V2 final. And I don't know either one of them. I don't know those. So it says, what is the velocity of the 2 kilogram particle? I do not want to get this wrong because I look at the wrong velocity. So I'm going to put a circle around that. It asks for the velocity of V2. It asks for the velocity of the 2 kilogram particle. So I'm going to put a circle around that. First part is momentum before is equal to the momentum afterwards. So then I come down here and I go 2 times plus 5 added to 4 times minus 3 is equal to 2V1, I forget the final, plus 4V2. I've drawn them both as in the positive direction, and I'm going to assume they are. And if I get a positive number for my answer, it means that I guessed right. And if I get a negative number for my answer, that means I guessed wrong, and I put the opposite sign on it. It's no big deal. If I guess it's going to go in a negative direction and I'm wrong, I get a negative of a negative, and that's kind of like, you know. So just assume it goes to the right. So then we turn around and say, okay, let's just do this bit of math. So this is 10 added to minus 12 is equal to 2v1 plus 4v2. So, and here's the trick that, you know, I learned a long time ago, which is if you want to find v1 final, the thing you need to isolate in your first equation is v2 final. You want to substitute in to get what you don't have. So I'm going to go across here and say 4v2 is going to equal, that's going to be minus 2 over 2v1. So this means that v2 is equal to minus 2 over 8v1. Did I do that right? Got a little alarm bell going off in my head. So minus 2 is there, and that's 2. So, yep, I think that's okay. That's not sufficient. I've still got an unknown. So what I do is I say, oh, yeah, the difference in my velocities before the collision is equal to the negative of the difference in my velocities after the collision. So I've got to keep the order. I can't just play with these things. So I'm going to say plus 5, I'm looking at my diagram, minus 3 is equal to the negative of v1 minus v2. Let's just rework that. 5 minus 3 is 5 plus 3, so 8 is equal to, let's change these two around. v2 minus and minus makes plus, minus v1. I'm going to substitute in that guy there for into that equation. Well, let's rearrange it first. Well, no, let's not rearrange it first. So I'm going to say 8 is equal to, I'm going to substitute in 4v2. So it's going to be minus 2 over 8v1 minus v1. So I swear I've got a problem here. Let me have a look at this. 4v2 over v1. Let's have a look. Minus 2. Oh, I divide. Bonaquisti. I'm sorry. So let's get my eraser. Yeah, can you see how my alarm bell was going off? And so what did I do wrong? What I did was I transcribed something just incorrectly. So if I have this, I have 10 minus 12 is minus 2. I have my V4, took that, I've got to take my minus 2 to the other side. And this is going to be minus 2V1. Agreed? So it just shows, you know, it's kind of like, don't think that, it's not that you can never make a slip, but it's that you want to set up systems where you catch slips, you know. And so I need to set up a system where I catch slips. So V2 is equal to 2 minus V2V1 over 4. Did I do that right? Yep, minus and minus. So I'm going to just double check that again. So that's minus 2 minus 2V1. Yeah, that's right. So now I come along here and I substitute in. So I need to do a bit more erasing. So now let's go along here. So then I go, okay, so I have 8 is equal to, and I want to substitute in for V2, so it's minus 2 over 4 minus 2V1 over 4 minus V1. Okay. Let's have a look. So that's going to be 8 plus 1 half. Take that to the other side. Is equal to minus 1 and 1 half V1. Minus and minus, so minus 1 and a half V1. That's 9 over, sorry, that's going to be 17 over 2 is equal to minus 3 over 2 V1. The 2's go away. So V1 is equal to minus 17 over 3. So V1 is equal to minus 5.66 meters per second. Can I just double check on that last bit? So let's have a look. I substituted in. I said, let's have a look. 5 minus 3 is that. So 8 is that. So 8 equals minus 2 over 4. I think that's right. Is that right? Oh, the answer's there, so it must be right. Yeah, sure. Okay. So, just 2 equations, 2 unknowns, do a substitution. Just a 2-step problem. But, I mean, I suppose what I think was more telling in that is, I knew there was a problem when I was multiplying my v, and there was going to be a v squared. And I knew there can't be a v squared in this. So my alarm bell had gone off before, and that was like, no, there's something wrong. You've got to go back. And it was just a math slip. But just math slips count. So you gotta build into your system enough that you can spot errors and you can correct them. And with respect, I think that means writing more down. I think if I'd have only just been doing that in my head, I wouldn't have caught it. I'd have just gone on. Questions? Okay. 4 kilogram particle traveling with a velocity. Ooh, so 4 kilogram particle. 4. Traveling with a velocity of 2I plus 3J plus 4K meters per second. Collides with a 2 kilogram particle. And that's got a velocity of 2I minus 4J plus 2K. I'm not making any attempt to get these arrows in the right directions. I'm just figuratively representing velocity vectors. What is the velocity of the combined mass after this perfect inelastic collision? So I told you that the 2 stick together. So afterwards, I'm going to get, and it's going to have a certain velocity, and this is 4. And this is 2. So I go from those 2 down to that. So I say, oh, well, yeah. P initial equals P final. So M1 V1 initial, and that's a vector, plus M2 V2 initial, and that's a vector, is equal to M1 plus M2 V final, and that's a vector. Oh, I know how to do this. I'm just going to say I, J, K. The first thing I want is M1 V1 initial. So I look here and I go, that's an 8, and 4 times 3 is a 12, and 4 times 4 is 16. So you see where I got that from? I worked out my momentum for this first object. And then I need a momentum for my second object. I need M2V2 initial. That's just these ties multiplied together. So that's a 4. And a 2 times a minus 4 is a minus 8. And the 2 times a plus 2 is a plus 4. And that tells me to add So I'm going to go 12I, 4J, and 20K. So that's that right-hand side. And to get my VF, I've got to divide it by, so I'm going to go M1 plus M2, and that is 4 and 2, 4 plus 2. So V final is equal to 12 over 6I plus 4 over 6J plus 20 over 6K. So V final is equal to 2.0I plus 0.67J plus 3.33K meters per second. And that's going to be one of those first ones, a 67, 66 I put down. It's C is the answer. I would not ask you to do IJK on a elastic collision. I would actually I might do it on an inelastic collision. It's a bit more work though. It's a longer question, so this is the one that lends itself easiest because there's fewer steps. But it's elastic collisions are fair game. But IJK is fair game within that context. Okay. I'm going to do in 8 minutes. Good. Okay. This next bit is not needed for this chapter. It's needed for like future chapters. So they bung it in here, and it's so we've got a complete change of mindset. We've finished with collisions. We're going to have a complete change of mindset. We want to go on for rotation. That's the next chapter. And things rotate about their centre of mass. So we need to be able to find out where the centre of mass is. It's like, we need to be able to do it. The next chapter, I think, tends to be a bit long, so I can't remember if the book put it in here or I put it in here, but it's here. And we've got basically 3 physical situations. We've got one physical situation where we're all in a line, so I don't need to worry about directionality. And then we've got a second situation where we're actually in 3-dimensional space, so I've got to take into account vectors. And then the third situation is we don't have individual masses. We have a distributed mass. So if I have a set of papers, I can find its centre of mass by, you hang it basically, you hang it and you draw a line under the hanging point, and you draw a line under the hanging point, and where those lines cross, that's the axis for your centre of mass. And you can tell where the centre of mass is because if you throw it, things spin around their centre of mass. You can't throw a pen and have it rotate about the cap of the pen. It's not going to do it. It's going to rotate about the centre of mass. And so we need to be able to calculate these things. So we just work through them. So we have, let's take them in a straight line. If they're in a straight line, then we come up with a generic equation, which is x centre of mass. That's not centimetres. And I've taught this for years, and then last semester somebody was putting their answers in centimetres. I said, why are you putting centimetres? Well, it says x centimetres. It's centre of mass. So x centre of mass is equal to, and you've got to wonder how many times people have done that and been confused and just never asked. And it's like, it's quite logical, xcm, you think it would be centimetres, but it's centre of mass. I need to change the case on that to big C, big M, and then people won't think about it so often like that. And it's for each mass, it is the sum of each mass times its position on the x-axis divided, when you've done that sum, by the sum of all the masses. That's not justified, it's just done. And then later on we'll do 3 masses or 2 masses or whatever that are not in a line. And we find that it's actually not that different. Now if we have the vector going to the centre of mass, it's the sum of each mass times its displacement vector. And when you've done that summation, divide it by the sum of all the masses. And then if we go to a distributed mass, like a cloud of atoms, then we end up with an equation that on the face of it looks somewhat different, but it's just the way it's traditionally written. The integral, rather than having the sum of all the masses, I have the integral of all the masses, then that's 1 over m. That's just the same. And rather than having the sum of the mass times the little r, we have the integral of r dm. Okay, so it's kind of similar. You can work through it. 2 kilogram mass is located at plus x. So let's draw ourselves a diagram. There's my origin. This is 2 kilograms, and this is 5 meters from my origin. 3 kilogram mass is located at, inside. 3 kilogram is at 4 meters. Where's the centre of mass on this axis? And what we said was the x position of your centre of mass was equal to the sum of each mass, that's mi, I going from mass number 1, mass number 2, mass number 3, mass number 4, times its position xi over the sum of mi. So I look at this and I got 2 masses. So this would literally be that my x centre of mass is equal to, well, I'll take the first mass. Let's take the 2 kilogram. So it will be the 2 kilograms multiplied by the 5 meters. And I got to do that for all the masses. So for the next one, it's 3 kilogram multiplied by 4 meters. And there's no other masses, but if there were more masses on this line, I just keep writing them down. Mass times position from the origin. This tells me to sum them, so let's put a sum sign in. Let's add them up. And then the bottom line says, add all the masses together. Well, we had a 2 and we added it to a 3. So that's going to be 10 plus 12 over 5, which equals 22 over 5. So x centre of mass is equal to 4.4 meters. Positive 4.4 meters, because it's, yeah. And isn't that what you'd expect it to be? I'd expect it to be in between the 4 and the 5, because one's at 4 meters and one's at 5 meters, and closer to the 4 than to the 5. So not 4.5 or 4.6 or 4.7, but 4.4 or 4.3 or 4.2. So it intuitively makes sense. I can decide to put my starting point wherever I like. So I just started at the origin because that's the information I was given, and I've got the distance from the origin. So this is x equals 4.4 meters relative to origin. And that just seems to make sense. I could, I suppose, have done it by putting my starting point somewhere else, and I'd have found the distance relative to that different starting point. But then to answer the question, I'd have had to go back to my, my axis, which had 0 on the origin. Do you see what I'm saying? Yeah? No? So, can do that. Next level. 2 kilogram mass is located at 3i plus 4j plus 2k, and it's a displacement, so call it meters. and a 3 kilogram mass is located at 0, oh, I'm looking at the answer, I'm sorry, minus 2I plus 3J minus 2K meters. Let's have a quick look. 55, I can just about do this. So then I say, okay. In fact, I'm gonna